Alright, so now we're going to be talking more about some statistical mechanics. This is, again, taught by Leonard Susskind, and I am sort of teaching this in a way to concisely put his ideas and the topics that he teaches within statistical mechanics within sort of a shorter time frame, so that you don't get the tangents and you don't get him answering the questions from the people in his audience. And so in this talk, or in this discussion, I want to sort of introduce ourselves to a very useful formula for the entropy of a system, right? And so what we went over last time are a couple of general principles, or a couple of general rules about the laws of probability, right? So the first one that we went over, again, increase the thickness of my pen right here, is this general rule here is that the sum of all probabilities within a system has to equal 1, right? So the sum, we talked about this in terms of distributions, or probability distributions, which is that every point within your probability distribution, when added up with every point, has to equal 100%. In other words, this statement right here is the statement that says, what's the probability of seeing anything within your system at all? Right, so that's the sum of all of the probabilities that correspond to each state of the system, and that has to be 1. So it's 100% that you will see anything at all, any sort of state within your system at all. That is what this general rule means physically. Right, so this is the first general rule that we sort of talked about in our first video. We also covered this general rule here, which is that, again, it's not really a different rule, right? This is just looking at it pictorially. Again, these are summing things up, but something a little bit more distinct here. The reason why I'm putting this under a separate rule is that with states, right? So we have heads, tails, heads, and tails. Corresponding to each one of these states, we can assign a particular energy, okay? That energy can be any number you want, right? So in this case, the state heads is going to have energy 8. 8 so 8 joules, say, right? We can invent a unit of measure, right? 8 joules. And then for heads, tails, we have an energy of 3 joules. Tails, heads, we said was indistinguishable, or in this case is indistinguishable from heads, tails. So that, again, is also going to be 3 joules. If they are distinguishable, then the energies could be slightly different. And we could talk about what this is known as degeneracy. The degeneracy of this particular state is 2, right? In the case of distinguishability, and then we have tails has an energy of 1. Okay, again, we're graphing the probabilities here, not the energies. So and what I'm going to do here is I'm just going to move this a little bit just to make that look a little nicer. And so the probability, again, of heads is a 4th. Probability of heads, tails, or tails, heads is going to be 1/2. And tails is going to be 1/4, right? Again, add all these together, and we get this general rule up here, right? Which is that the probabilities have to equal 1. We can see that here, 1/4 plus 1/4 is 1/2. 1/2 plus 1/2 is 1, so that checks out. Next, so we now kind of want to take this idea and we want to apply it to statistics now, right? So this is almost like the introduction of statistics into probability. So we say each state has some corresponding energy to it, right? So what is the average energy of all the states that we could expect in the system? And the way to do that is you basically take the energy as a weight of the probability, or a probability as the weight of the energy, either way, right? And that's right here. So in this particular case, the probability of state 1 is a fourth, right? So that's right here. Probability of state 2 or 3 is going to be a half, okay? And the probability of state 4 of tails is going to be a fourth also, right? And so we have this, so we have 1/4 of 8, right? So 8 is the energy corresponding to state 1, and then 3 is the energy corresponding to this state right here, heads, tails, or tails, heads. And then we have 1 here as being the energy corresponding to tails, right? So sort of, if you were to think about this pictorially, right, we have like these they're like these little name tags, right? These name tags tell us what the energy of each one of these are, right? Not the probabilities, because the probabilities are already plotted out here. We're looking at energies now, right? So if we were to calculate all this out, we get 2 plus 3/2 plus a fourth. Doing all this math, we get 3.75, okay? We can see, so that 3.75 is, we have, if we were to draw out our energies, right? So we have on a plane here. So here's 0, here's 1, 2, 3, 4, 5, and then 6, 7, and 8. Not really to scale, but so we have a point here. This is our state 4, P4. This is an energy axis, right? And then we have here, which is P2 is equal to P3, right? So this is the probability of P2 and P3. And then out here is the probability of state 1, okay? And what we just calculated right here is 3.75. Where's that? That's about right here. That represents the average energy of the system. If our energies are this. Now you can play around with different energies. And you could also maybe play around with what would happen if 2 and 3 were made distinguishable from one another, right? And in this case, you could play around with that and you could see exactly what happens. So this is the general principle here, is that the sum of for any system, for any system of states, there's a probability distribution, right? So that's what we were talking about initially in our first 2 videos. And if each state has an energy, so each state has an energy attached to it with a particular number, right? It doesn't have to even be an energy, right? It can be a number that's, say, associated with the momentum of a particle, or it can be a number that's associated with its velocity or its mass, right? It doesn't have to be an energy, but energy is going to be particularly useful when we start talking about statistical mechanics. Anyways, each state has a particular energy, then there is an average energy for the system of that state as well, and that average energy is given by this equation, okay? So next, we're going to want to talk about some important equations that sort of, given the rules that we've established so far, we're going to write them down, we're going to summarize them, and we're going to continue going forward with some more of the mathematical preliminaries before we dive in to some really interesting mathematics that governs the way we perceive statistical mechanics and how we can do physics within the realm of statistical mechanics as well. Again, if you like my videos, you can subscribe to my channel, you can visit my Patreon page. And with that, I will leave you guys about 5 minutes to spare here. So I'll see you later.